Okay, well, let's turn to our first example problem, a particle in a three-dimensional box. Hold on for a second. Okay, let's take a look at it. In the three-dimensional particle in a box, our particle is confined to a region of space in the shape of a cube of dimensions L by L by L. And the particle is free when it's inside the box, and it's confined strictly to the box. In other words, the potential energy as a function of position is zero for x between 0 and L, and y between 0 and L, and z between 0 and L. And outside of this region, we imagine that the potential energy goes to infinity, just as before. Okay? Now the problem is solving this differential equation here for this example. In general, solving that differential equation is hard because this is a partial differential equation in three variables. However, what we'll see is that for highly symmetric problems like the one that we're about to solve, we can use a trick called separation of variables to break up Schrodinger's equation into three ordinary differential equations, which are each much easier to solve, okay? And this example is a good one for introducing that idea. So let's take a look, okay? 1 second. Okay, our solution is that we'll assume that the energy states, the standing wave states for this potential, are separable. And we'll try to find solutions of that form. And what do I mean by separable? I mean that the wave function can be written as a product of three functions, one that only depends on x, one that only depends on y, and one that only depends on z, which I'll call capital X of x, capital Y of y, and capital Z of z, okay? And if we substitute this separable solution back into the Schrodinger equation, we'll see we can break it up into three ordinary differential equations, okay? And let's go through that together right now, because it's interesting, even though we're mostly concerned with the answer, not so much with the process here. So the first step is to substitute this into Schrodinger's equation. And that gives us the following, okay? So now, now we'll have the second derivative with respect to x of the wave function, second derivative with respect to y of the wave function, plus second derivative with respect to z of the wave function. Now, when we do that, because we're using this separable solution, we recognize that each part of the wave function only depends on one variable, and so we can write it like this. For example, second derivative with respect to x is just the y function times the z function times second derivative with respect to x of the x function, okay? Because since these are partial derivatives, the partial derivative with respect to x doesn't act on the y and z variables. They're like constants. And then likewise, we have this, x, z, d squared, dy squared of the y function plus x, y times second derivative with respect to z of the z function, okay? The next step is to divide both sides of the equation by x, y, z, by the wave function, okay? And that gives us the following. Oh, I only wrote the left-hand side of Schrodinger's equation here, but let's go on. That's going to give us the following: minus h bar squared over 2m times, and when we write this, we'll have, I'll just focus on the left-hand side once again. And let's just look at the first term. And you'll see that when I write it this way, that the y and z functions will cancel out. And we'd be left with just the second derivative of x divided by x. And continuing, we'd have two more terms on the left-hand side. And instead of writing all those out right now, let's just skip to the next line, where we have a second derivative with respect to x of the x function divided by x, plus, and the next term would give us second derivative with respect to y of the y function divided by y, plus second derivative with respect to z of the z function divided by z. And on the right-hand side, we'll just have the energy. Remember, the potential energy is 0, and we've just divided by the wave function and canceled that out from both sides. Maybe I can just write that here and simplify my notation a little bit. Okay. And here, I'm just going to write this schematically. Well, this looks a little messy. So let me rewrite it in the following way. This is just to make it easier to look at for us. There. Where here I've used double prime to mean the second spatial derivative with respect to the important variable. So in this case, x double prime over x means second derivative of x with respect to x divided by the x function plus second derivative of the y function with respect to y divided by y, and so on. But I've done this for to make things look simple because I want to make an important point. This first group here, x double prime over x, it's clear that it can only possibly depend on x. Right? And likewise, this one can depend only on y, and the third one, z double prime of z, can only depend on z. Okay? That's pretty obvious. And then they add up to equal a constant. But in fact, their behavior is even simpler, because it turns out that not only can each of these terms depend only on one variable, but in fact, each one has to be constant, independent of x or y or z. Because imagine the following. Imagine that there was a particular value of x, y, and z for which this formula was true. Okay? And now imagine that I change only the value of x, but keep y and z constant. Well, the formula still has to be true, right? And so that would mean that the value of the first term, x double prime divided by x, actually can't depend on x. Because if it did, the formula would no longer be valid when we change from one point in space to another. But since it has to be valid everywhere, that term must be constant. And likewise for the other terms. Okay? And that's the secret, because now we have 3 terms and each of them has to be equal to a constant. So let's write that out. So we can say minus h bar squared over 2m of x double prime divided by x is equal to a constant. I'll call the constant ex. Likewise, minus h bar squared over 2m y double prime divided by y is equal to another constant. I'll call it ey. And we have a third term as well. And finally, we know that ex plus ey plus ez must equal the actual total energy, E. Okay? So now we've broken up our partial differential equation into 3 equations, okay? Which might be easier to solve. In fact, let's just rewrite these slightly. For the first equation, let's multiply both sides by the x function, okay? Then we get minus h bar squared over 2m times x double prime is equal to e sub x times the x function again. And likewise, we have minus h bar squared over 2m times y double prime is equal to e y times the y function. Okay, so now we have 3 ordinary differential equations. Each of which is much, much easier to solve than our original problem, okay? Pretty cool. We were only able to do this, going back a little bit, because we knew that there had to be solutions that looked like this, that were separable. And we only knew that we were able to do that because we saw that our problem had rectangular symmetry, okay? Rectangular Cartesian symmetry, meaning that there have to be solutions that have the same kind of symmetry. And that's what these separable solutions are. Okay, having done that, the problem actually becomes easy to solve, because now we can introduce the boundary conditions and see that these equations we've written here are actually ones we've already solved, okay? So because this is a particle in a box type of problem, we know that x of x has to go to 0 for x less than or equal to 0. I'm sorry. Or I've written that completely incorrectly. Let me just fix that. Sorry. And it also has to go to 0 at x greater than or equal to L. Okay. Likewise, the y and z functions have to go to 0 when y reaches 0 or y is equal to L. And the z function must go to 0 at z equals 0 and z equals L. Okay? Now, once we've done that, you might be able to recognize what we have. Looking at the first set here, what we have is just this problem here, this equation here, and we're looking for solutions that have the property that they go to 0 at x equals 0 and x equals L. But this is just the original particle in a box problem, okay? So we know what the solutions are. Each of these, the x function, y function, and z function, they all look like particle in a 1D box problem. And so that means we already know what the solutions are from the work that we did before. Okay? So in particular, the solutions are x of x is equal to some constant, let's call it a, times sine of n. Let's write it this way. N sub x pi x over L. Okay? Y of y is equal to some other constant, b, times sine n y pi y over L. And z of z is equal to some other constant times sine of n z pi z over L, where n x, n y, and n z are each quantum numbers that can take on values 1, 2, 3, and so on. Okay? We know that because each of these problems, the problem for the x function, the y function, and the problem for the z function, they all look exactly like the one-dimensional particle in a box. But that's not all. In addition, we know that Ex can be written as h squared over 8m L squared and x squared. And so on for Ey and Ez. Because once again, those are the energy, those are the solutions for the one-dimensional particle in a box. Okay? And finally, putting these together, we're going to get equations for the wave function and the energy of the three-dimensional particle in a box. The wave function looks like this. Psi of r is equal to, we can normalize each of the wave functions as well. We're going to get is that a is equal to root 2 over L, b is also root 2 over L, and same thing with c. So we have 2 over L, multiplying them together, we get 2 over L to the 3/2 times sine of nx pi x over L times sine of ny pi y over L times sine of n z pi z over L. Okay? Whew. And then we have a formula for the energies as well. And the energies are given by h squared over 8m L squared times nx squared plus ny squared plus nz squared. Let's put a box around these solutions. There we go. And let's stop here for a minute.